So welcome back to the introduction to cooperative communications and prisoner dilemma. So in the first part, we will look into cooperative communication architectures. If you remember the football stadium and if you see the different red arrows we had there, this is the kind of topology we look into that. But the nodes and the topology, they have different roles, and this is what we would like to look into here. So first of all, so far, I think most of you have heard about centralized approaches. Now we are talking about a distributed approach. And communication networks normally are based on protocols. And if you have a centralized approach, so some boss in the middle, like a base station, then this protocol design is pretty easy. The internet itself is already distributed. You can learn a lot of these things, but in a very agile situation, like for example in the football stadium, even the distributed approaches from the internet are not always working. And if you come to distributed, there will be always less degrees of freedom, and there's more to do than only a point-to-point communication. I already mentioned that there will be centralized cellular and centralized cooperation scenarios, and we come to this later. And what is also interesting, there's this term self-organizing cooperative networks. So if you don't have a centralized entity, who will rule about what to do in the network? And how can you spawn, for example, cooperation in your cooperative cluster? So we need to think about the protocols and how we can tune them and optimize for collaboration, or how we tune the protocols to let the users see that their own selfish-oriented performance will increase if they cooperate. So here you see different relaying architectures. The first one, we took this out of the book, as you can see here. One of our colleagues wrote about fundamental limits and practical implementation. And you see here something about different architectures. One is really the direct link, point to point. You have a source and a destination. The source is generating information and sending the information over a medium to the destination. The two-hop channel is the first collaborative scenario where you have a source, a destination, but this time the information will pass a relay because there is no direct link between the source and the destination, so all the information has to go to the relay. And this we refer to the two-hop channel because there are two hops here. There's also a relay channel. It seems a little bit like a combination of the two scenarios before. You have the two-hop channel as well as the direct link. Now, the role of the relay is very interesting. While in the first part, 100% of the information should be relayed, now the relay could be also do the same, sending everything you get from the source to the destination. Often we find wireless mediums, so it's a broadcast channel, and if the relay would just forward everything he has understood, because he's very close to the source, we assume he got 100%, then he would send a lot of information to the destination that have been already sent over the direct link. So there's something what we call redundant information, and how we can avoid these situations, because also for the relay there's a lot of things to do, and this forwarding will cost a lot of the energy. So here you have the three topologies: direct link, two-hop channel, and relay channel. It becomes a little bit more complicated later, but first let's identify that this to the right architectures are have two cooperative clusters, right? And you will see more cooperative clusters later on. So you can make it more advanced. If you have a multi-hop channel, not two-hop, now a multi-hop, then you have a chain of relays between the source and destination. Still, there's no direct link between source and destination. And you can have also multi-path relay channels, where you have a direct one and multiple relays. And now we could even combine this with multi-hop and multi-path relay channels if you want. Here again, you see the cooperative clusters, and this is something that you can also identify within the football stadium, right? So far, we have clear roles for the nodes. There's a source, a destination, or a relay. But as you can see here, we can also make this a little bit more interesting. Before we do that, there is also some questions in this kind of relaying scenario, right? A relay could always ask, why would this relay be interested in helping source and destination? What is the benefit of the relay, right? And if you have two of these relays, how can we make use of two or even multiple relays in an efficient manner, right? I already told you that there might be redundant information that come to the destination. The more multipass you do here, the more redundant information you will receive at the destination. Something that is often referred as a coupon collector problem, right? Maybe we come back to that in a later state, but very interesting. To make this efficient, you need clever protocols and approaches how to relay. But still the question is, why a relay at all should relay information? So I told you already, the roles can also change. So if you have a source, in this case, that could broadcast information, that could be, for example, a base station where information is received and then conveyed in a broadcast fashion to multiple devices, and then these devices will share the information. And now you see this looks pretty much the same that we had as an example in the football stadium. And now you don't have clear roles like a relay or a destination, because there might be a lot of nodes interested in the information, but they also would relay it. And here's the first idea why this relaying would make sense. If everybody would listen to the source, only get a portion of the information, later the exchange will help to make this situation better. So if you as a node will lose packets from the direct link, you can ask your neighbors, can you send me just some packets to clean up my problems that I have? And as others would like you the same favor, there is already some kind of cooperation, and you see why cooperation could be spawned in such a scenario. We call this a one-source multi-destination. If you want to make it even more advanced, a node can be all three parts. It could be a source, a relay, and a destination. It's a multi-source, multi-destination case. So this is, for example, if you have wireless sensor networks with storage and everybody has a little bit of the storage and you have to bring it together to one of the nodes once the whole information is needed. Again, you see here the cooperative cluster. Why is this so interesting? Here you see the football stadium again. I told you on the left there is a different motivation for the relay and destination node. This part here is also interesting for us, because if you have heard about COMNETS 2, where we have softwareized networks with SDN and NFV, it's very interesting to see that these kinds of nodes nowadays in the softwareized world are easy to realize. Okay, and if you have larger and bigger networks, here we say source, relay, destination, a node can be everything. There are certain things that can happen to the network that are also interesting. So what happens, for example, if this big network breaks into parts, into three different parts? And you see already where the problem is. As we don't have a centralized authority, we need to understand, or the network itself has to understand, that certain services that were given in the big network, for example, one server running or a mobile edge cloud running in one of the nodes, once you break up, you have to spawn this kind of service in each of the different separated networks now. So first you have to identify the situation, and then you have to spawn a new service. Another thing is, once you have separated networks, what happens if they merge again? So now you have spawned three different servers doing three different things, how to bring them down again. So there must be a lot of information flow and organization in such a network in order to keep it alive and to make it efficient. And all of these problems are parts of the lectures you will see within this semester. Good. I will give you some more examples. I think the other one were quite generic. We have done a lot of work in relaying architectures, for example, for mobility. On the right side, there are these red nodes that are connected over a Wi-Fi scenario, and the numbers you see there, they are data rates. So in COMNETS 1, you have heard about data rates of IEEE 802.11, and the longer the distance between sender and receiver is, the lower the data rate goes in order to keep a certain SNR in your transmission. And you see that nodes that are very close together have 54 megabit per second possibilities, and others, they have 6 megabit. And this can change over time if the nodes are moving. So mobility plays a really big role, and the formation of the network will change. And also the kind of cooperation gains you will see in such a cluster will change over time. So the mobility has an impact on the data rate, also about the role of the communication node. As we have said, you can be a source, a relay, or a destination, sometimes even multiplicity of all three of that. And sometimes you're just a relay, sometimes you're just a destination. It will change with mobility. And we also said that we need to fulfill certain tasks in the cooperative cluster, and also this will change with mobility. And there are different applications for that. I brought you two videos here. One is the connected driving, one is the flying drones, and the mobile phone cooperation is something that we have done over the last decade, and there will be examples throughout the lectures. But let me start these two videos. I will just play them. The first is in German, and the other one is just showing you a product of one of our startups here from the chair.
In Deutschland wurde das Automobil erfunden. Jetzt prägen wir die nächste große Mobilitätsrevolution. Das automatisierte und vernetzte Fahren. Auf dem digitalen Testfeld Autobahn, auf der Bundesautobahn 9 in Bayern, werden Technologien der Mobilität 4.0 erprobt. Unser Ziel? Deutschland, das Land der Innovationen für den Verkehr, auch im digitalen Zeitalter. Auf dem digitalen Testfeld Autobahn werden hoch- und vollautomatisierte Fahrzeuge unter Realbedingungen erprobt. Dabei übernimmt das Fahrzeug die Führung vollständig für eine begrenzte Zeit. Vernetztes Fahren schafft eine neue Dimension der Mobilität. Fahrzeuge tauschen miteinander Informationen aus und kommunizieren mit der digitalisierten Infrastruktur. Durch den Aufbau der intelligenten Straße, die Daten über ihre Sensorik in Echtzeit liefert, wird eine Car-to-Infrastructure-Kommunikation ermöglicht.
So I hope you saw the first video that was a connected car scenario, where you also saw a little bit of the kind of cooperative cluster that the cars will have. You also saw how agile the movement of a car will impact the network architecture. And the last one was really a product where you saw some drones flying in a virtual world first with some multipass connectivity to keep the resilience. And later you saw also the drones flying there over a multiplicity of access points. There we did not have enough drones to fly this in a cooperative fashion. This is something they are doing at the moment, and Meshmerize, this first company that you saw here, they will also give one lecture about their success in the Meshmerized world. So I think it's both. You will hear a little bit about the theory in the beginning, and later you will find out how this really can be applied. For example, on drones. We are looking forward to hear about that. Now, I would like to talk next about the motivation to cooperate in an egoistic world.